Good evening, everyone. Welcome to the 11th session of Fundamentals of Additive Manufacturing Technology. So, today we'll be discussing on laser powder bed fusion. Powder bed fusion, and I'll try to solve some numericals questions from the assignments related to the powder bed fusion only. So, this is the main schematic of the laser powder bed fusion. So we will discuss what are the components here, and we will, based on this components, questions on assignments are present. So major component in FPBF process is the laser. Okay. So what kind of laser do we use in a generally a printing process? So laser may be one or two, even four is possible to improve or increase the productivity. Up to four lasers also we can use. So when we have more components, it will be efficient to print. So that is why we use more than one laser. So up to four lasers are commercially available. Power for this process up to 1 kilowatt is available. Up to 1 kilowatt. Type of laser is, this is by EOS Germany company. Type of laser is continuous wave yttrium doped fiber laser. 99% of the SLA 3D printers we use this laser, which has a wavelength of 1070 nanometer, 10 plus 10 nanometer. So life of this type of laser is 100,000 years. Life of such laser is 100,000 hours. This will be approximately 12 years, that is 24. This we say into that 24/7 if the printer is running. Okay. Some other types of laser are nanosecond, femtosecond. So these two lasers are not used commercially. These are used on laboratory scale, and these are used in micro and nano 3D printing. Now next thing is, how do we decide the power of the laser? How to decide the power of the laser? In a 3D printing process. So which parameters are used to decide the power of the laser? So first is our melting point. So thus till now we discussed on how many lasers can be used and what is the power required And then types of laser. There we discussed this is the laser which has been used in commercially till now. These two types of laser has been used in laboratory scale. Now next we are trying to understand how to decide the power of the laser. So first is our melting point. Okay, this is the most important point. Next is deflectivity. So if we take the example of titanium and aluminium, aluminium is more reflective because it has reflectivity which is occurring in aluminum is much higher than higher power. We need a higher power laser for aluminum 3D printing. So next this is reflectivity. Now again one more point is that if the oxidation tendency of one more powder particle is higher, then the power requirement is low. So when oxidation tendency in a powder particle is more, then the reflectivity will increase. Less power required as reflectivity is more. Okay, this is one more point. Next we have a laser correction arrangement over here. Correction arrangement. This is a galvanometer. It regulates the XY. So in XY plane, our galvanometer controls the positioning of the laser. Okay, this is the XYZ plane. Next we have the powder bed. Now in this powder bed, in this sometimes both side powder is available or sometimes only one side powder is available. So in this case, some extra powder will be overflowed on the right side. Next we have a roller. Roller, this we will discuss again later. Okay, now roller is of different types like blade. Okay, I'll just write blade, and this type of roller which is present here, this is the doctor type of blade of roller where we use the electrostatic forces. Electrostatic but for electrostatic mechanism case, the powder particle should be magnetic. Okay, now here in electrostatic mechanism we use the electrostatic forces to provide the single layer of the powder particles. Electrostatic mechanism. But we should take care of the point that the powder particle should be magnetic in nature. Otherwise, if that is not there, it's not possible. Next is we have base plate. Now in base plate can be heated. I'll write it here. Base plate can be heated or non-heated. And your powder bed may be heated or non-heated. If you are heated or heated. So in an electron beam, it's necessary to heat the powder. But if we are using laser, it's may or may, like heating the powder bed may or may not be required. Now, and why it is so? Because in case of laser, we are using the inert gases, but in case of electron beam, there is no inert gases. Now, some other properties of the build plate is it is supposed to be similar to the material. Like if we are printing Ti6Al4V, the base plate should be of titanium. Because it will be easy to form because it will be easier for the component to form the bond between the base plate and the formed material. Next, this I will write it here. Similar material of base plate and the powder material. Base plate and powder material. Now, this entire setup should be closed. If it is closed or open. If it is closed, then it is vacuum or it may use some inert gases. In laser powder bed fusion, we use inert gases like argon. But in case of electron beam process, we need to create a MAC. Now, this is in a chamber. Suppose in case of this is sometimes closed. Okay. Now this is in closed. Okay. Now open is also used. Open is for polymers. Closed chamber, we need to reduce the oxidation. Okay. But in polymers, there is no oxidation. So we can use open type of chamber. Okay. And roller blade, we will discuss few more things. Now roller blades we'll discuss. Roller blades, where I said you that this is a doctor blade. Okay. Now doctor blades of two types. Doctor blades, soft blade, hard blade. Now we have to understand what is the soft blade, hard blade, and when do we use it. The soft blade is made of carbon fiber, silicon or rubber. Design is similar to that of brush. Now hard blade made up of hard tool steel. Now hard blade is usually more preferable as compared to soft blade. This is because in case of soft blade, naturally the wear will be very high. So we have to replace the whole blade frequently. This will be costlier. But for some components it is necessary to use soft blade. Components necessary where soft blade should be used. These are like lattice structures, porous structures, now these lattice structures are very fragile. Okay, so like the walls may be of 0.1 mm. So in these cases we have to use soft blade as these are very fragile, so that when those blades will strike the component, it will not break. But if the hard blade is used, it will break the whole component. But in in but if we are using trying to build some other components like some aero engine components, we have to use hard blade, because the life expectancy of when hard blade is used, life and maintenance, life is more life and less maintenance. Okay, so now an assignment related to this positioning of the part, one question is there. So this is about the positioning. Okay, now in 3D printing we have a base plate. We will place it like this. Okay, mostly this happens in FDM, because in FDM we always place the component in center position. So because sometimes this may be a problem with leveling, so to avoid this we usually place the component in a middle portion. Now because here always inaccuracy is mostly less. Okay, it is always preferred to put it at the middle to avoid inaccuracies. This is for FDM what I am talking. Fused deposition modeling or fused filament fabrication. But in a SLM process, this all problems are not there, because those machines are itself very costly. Build plate is always leveled. So here what we have to do is we have to reduce the contact area between the reporter blade and the component. Okay, reduce contact area between reporter blade and component. Now, how do we decrease this area? Suppose the reporter bed is moving like this. Okay, this is the reporter bed. Now it is in contact only in at this position. This contact at this position. Sorry. So this is the only point of contact. There is no abrupt contact between the part and the reduced blade. So this reduces the possibility. So this reduces the possibility of component failure. This is the motive behind placing the component in an unbalanced manner. with respect to the recoater blade. Now this is we are seeing from the top view. Okay. Now if we see it from the side view, if we see it from here, side view, this component will be like this. This is the supports we are providing in theta. This is the theta angle. Okay. But we do not usually go for this position because we have to provide supports. So we usually do in XY position. This is the optimum. See, what happens is why we are tilting in Z, because only what one point we are having contact. So that is why this is the optimum. But we usually do not do to avoid supports. But this is the way we reduce the force from the recoater blade to the components, to the part of component, whatever. Now, what will happen in case of multiple components? We'll understand. Now, multiple component we have to place like diagonally. We do not place it in a this manner. This is never recommended. Now, we can see that there is an angle in the XY plane. This is the angle. Now all these components are aligned in a diagonal fashion. Now the reason behind to do this type of arrangement is that to decrease the force. First reason is decrease the force. Reason for this arrangement, we are decreasing the force. Now when we are second is, suppose we are placing the component like this. Now if there is distortion in one, this 1, 2, 3, 4. Now recoater blade is coming, it will break some of the part of the first component, and this broken portion will go to this second one. Now the first component is also inaccurate and the second component will also be inaccurate. This may also go to the third one. But if we arrange it in this diagonal manner, then if one in first component distortion is there, this will not be carried to the second or third or fourth part. The broken component of the first part will not go to the second part or third or fourth. This is the second reason to arrange it in a diagonal fashion. Now the function of the, what is the function of the recoater blade? Recoater blade will whenever there is a contact between the part and the recoater blade, the process will stop automatically. Like suppose if there is some distortion in your component, it will stop. So as we know, the cost of printing is very high. So if our component is inaccurate, it is always wise to stop the printing of the component at that point itself. So rather than going for the entire faulty component, so it is better not to waste and stop when initial 20 or 30 or how many percentage of printing has been completed. So this is the function of the recoater blade. So first is some more. This is a major function. Other functions are like provides uniform layer of powder particles. Now, along with this, similar to this from the three-quarter blade, one more question is from your assignment is roller is there. One is clockwise, one is anti-clockwise. Clockwise, anti-clockwise. Now, the question is, if we rotate the clockwise and counterclockwise direction, the uniformity of the powder particles is better. So in 3D printing process, the direction of the roller is always in the anti-clockwise for uniform. This is the reason. Just a second. Okay. Yeah. So this was about the reporter blade and rotation. So that is so the direction of the roller which is moving forward is always in the anti-clockwise. Okay. Okay. Yeah. Now this is about the component distortion. Okay. So here we can see some of the problems in the 3D printed components. So in gen so these so here generally these type of errors are generalized as delamination, but this is not a delamination. Delamination, support clacking, and flaking. Okay, so this is delamination, sorry, support clacking, flaking. Okay, so regarding this also some questions are there in your um, assignments, like yes, any doubt? Slides are not visible. Okay, okay, okay. Let's see. Fine. So this is now here we are seeing delamination, support clacking, and flaking. Now one question related in assignment is related to supports also. What is the question is like function of supports? Does it reduce delamination or some other kind of or some other kind of functions are there? Now, function of support structure is to provide support to the hanging components. So, apart from this, some other thermal functions are there, but that is not in our options. Okay. So, from here, we can see the difference between the delamination. Okay. We have this component. Suppose we have this component, and the crack in the component is in between the component, like this. Okay. So, this is a delamination. So this happens by using improper process parameters like scanning speed is high, we are not using a heated chamber. For all these conditions, these type of problem, usually this condition happens. Okay, next is, so this is not this doesn't occurs in FDM printer. Usually it doesn't occur in FDM process. Exception may be carbon fiber, uh, which needs to be printed. Carbon fiber delamination may occur because temperature requirement is higher. If you print at lower temperature, this may occur. Now, some other problem in the SLM printing is support cracking. See, we can see in the bottom we have supports. These are all supports. These are supports. Okay. But the area of contact between the support and the component is less. We are using these small pillars, so this area of contact is decreases. But it can create a support cracking. So this type of problem is known as support cracking. Other next one is flaking. Flaking is somewhat similar to warping, which we see in polymer processes, but see, like here the side part is lifted. Lifting is there. This connection is there between the removal of the, there is this connection between the base plate and the component. So these are three different methods: delamination, support cracking, and flaking. Now we have this improper bonding between the supports. Like here we have an improper, at the intersection of the component and the support, the component has split. Okay, support structure failure is there, and dimension of the final product will be different. Okay, now here also we can see titanium component, it is the base plate. So here there is a delamination between the component. Okay, this part is the delamination. Now methods to reduce these problems are optimum laser speed, heated chamber, okay, these are the methods to reduce. Next is, we move on to the next slide. So here we have some questions on joining mechanism. There are these three different types of joining mechanisms: sintering, liquid phase sintering, and melting. So you can see the phase difference. So we have to find out the difference in quality of the product that we get from all these processes. Now, in sintering, the temperature is between half of the melting point of the melting point and to the melting point. Okay, suppose we are printing an aluminium alloy, ALSI 10 mg. For this, melting point is 575 degrees Celsius melting point. So we have to use a temperature higher than 300 degrees Celsius. So this is the main parameter in sintering. So in sintering there is no actual melting of the powder particle. Here fusion of these necks occur. These necks fuse and form. Now, in the commercially available 3D printers, we prefer to use a spherical powder particles. This is most preferable. Spherical. Nowadays, few studies are coming where we can use irregular geometry powder particles also. So they are also giving better mechanical properties, but this has not been commercial till now. Okay. Uh, the reason to use a most of the powder particles which use in SLM process are uh, they use gas atomization process. Now in gas atomization, the resultant powder particles which we get are spherical. Now sintering, these are the three different stages of sintering process. First we have the unsintered powder particle. Okay, suppose we have these 4 powder particles. When we increase the temperature, there is a partial breakage. Okay, fusion between, this is the fusion between the intersection of these powder particles. So it is starting to form a bond. Okay, as we increase the temperature, again these pores will start to decrease porosity and increase necking. Necking means fusion or bonding between the particles. Okay. Okay. So this is the process which is followed in sintering. Now just imagine this will more adjacent particles will be there. This process will keep continue. Ultimately, the density of component in sintered product is less. Suppose we are using a titanium component, the density of the 4.4 gram per cc, but the ultimate density of the powder that we are getting will be, it won't be 4.4 gram per cc, it will be lesser. So this is the problem usually which occurs with sintering, density decreases. Next is, to improve the performance of the sintering, we can use some kind of liquid phase. Suppose we have a powder particle where we have an example in assignment also, where we have nickel and tin. Which one is liquid phase or bonding phase, or which is the main component or powder particle? So here nickel is the main structural component, and this is liquid phase agent. This will increase the reaction that happens during the sintering process. It will increase the rate of reaction during the sintering process. The melting point of the tin is much lower than the nickel. So when the temperature is increased, suppose 200 degrees Celsius, this will be molten form. So this will increase the wettability of the powder particle. Ultimately, sintering quality of the inter product will be as higher as compared to normal sintering. That is why we use liquid phase sintering. So it is so we can also use a lower temperature so that here we can use a lower temperature in liquid phase sintering as compared to sintering process. It may be possible that we can get the same quality at a less temperature in liquid phase sintering. Now the third thing is melting, or this is selective lesion melting. Here no external phase is there, nothing is there. We have the powder particle, and we'll provide a laser power in such a way that it will melt the powder particle. And if the melting is happening in powder particle, so the density of the product is much higher than the other two processes, sintering process and liquid phase sintering process. Okay. Now there are different steps in liquid phase sintering. There are two different routes. We'll see in the next slide. Okay. So there are two different routes with direct route and indirect route. Okay. So here we have the discussion of indirect route. So we will write about direct route. This is only single structural powder. So here there is no other type of liquid phase or anything. Now indirect route is also there. Now first here in indirect route we will have a loose powder. Then we have a these are maybe metal ceramic particles mixed with polymer binders. Now why polymer binders? Because melting point of polymers will be lower around compared to that of metals. Now this is the powder bed fusion processing. Now in this melting and resolid of polymer binders enable complex parts to be formed without thermally affecting the metal or ceramic parts. Okay, this means that in case of sintering, we have to choose the temperature half of the temperature between melting point and Tm by 2 or 2 Tm. We have to choose the temperature between that. So what will happen is quality of the final product, there will be a lot of residual stresses in that. So if we use polymer binding along with it, this will decrease the temperature requirement, and thus eventually if the when the powder particles are subjected to high temperature, there will be comparatively residual stresses, less residual stresses. So in those so when we use polymer binders, this decreases the temperature requirement. Now this type of specimen or component which we get out of 3D printer is known as green part. Now after removing these polymer binders from the 3D printed component, that is known as the brown part. And after that with increase of in this finished part, there is no polymer left. All the polymers is removed in the brown part. Now the sintering happens between this green part and brown part. Okay, where the polymers will vaporize. Now the problem is this type of processes. Problem is, see, this is a selective laser sintering, green body and sintered part. Okay. Okay, this is a selective laser sintering process. This is the fused filament fabrication process. Okay. Both these material is same. Yes. Now here we can see the quality is much better as compared to the in selective laser sintering is much better than the fused filament fabrication is not good. Okay, because this is a very cheap process and this is a costly process, and where we use powder particles. Ultimately, the now other problem is the dimension of the green body in center part is different. Okay, there is a lot of shrinkage. So this shrinkage why it occurs? Because evaporation of the binders occurs. Okay, so for these, okay, for suppose if we say the this is for dog bone, plain simple dog bone shape components, if such shrinking occurs, it may not matter. But for complex geometries, if shrinkage occurs, okay, suppose we want to print turbine blades, for that complexity is much higher. So we cannot use such processes in this type of because the distortion of the curvature will be much higher. It won't be possible to control the deflection of the three different planes. So we do not have any software to give the tolerance for this type of complex components. For those cases, we have to use the SLM process. Okay. We can use DD process or SLM process. Okay. Simple components we may use such process, but complex component we should use DD or SLM process. Okay. Now in we know that in SLS process the microstructural property will be better in SLS process. Okay. So this was about some theory questions which I have covered through this concept. Next we'll go to some questions. Okay. So the first question is which of the following it is clearly visible, right? Okay. So this is the first question. Which of the following is correct for indirect route of okay, we discussed this concepts now. So we will solve it. Okay. So which of the following is correct for indirect route of selective laser sintering? So in just now we discussed about direct route and indirect route. So in the first option is laser beam melt or center the powder particles with desirable material on the powder bed itself, and laser beam does not melt or center the powder particle. So option B, final part is produced by post processing of the green part. This is correct. So this option A, B and C is correct. Okay. So the first one is for direct and last one is also direct. This is for indirect and this is for indirect. Okay. We can say, suppose I will also give one more example. We have this powder particles and consider this is your polymer. Now this will be processed. Okay, this will be processed from green part to brown part. This is the mixed powder particles which is followed in indirect route. Okay, next question. Which of the following are usually considered for powder material for indirect route? Okay, so this we just covered now. Now thermosetting, thermoplastic we all know. uh, about some thermoplastic. What is thermoplastic? This can be repeatedly heated to soften or melt and cool to solidify as the temperature passes through Tg and Dm. Now, for indirect SLS, we have coated powder particles. The coated powder particles, this will be of thermoplastic polymers. This may be ABS, acryl, nylons. Okay. Now, thermosetting polymers are epoxies, polyamides, phenolics. Elastomers are rubber, silicons, polyurethane. Okay. Now, coating is made up of material which has a very, in indirect SLS, we have coated powder particle which is made up of material which has a very low viscosity. Okay. So, these are the materials which can be used for powder material for indirect route. Now, which of the following are advantages of SLS? Now, SLS, no support mechanism is required, capable of building functional part is essential in essentially fine materials, and uncured material is easily removed after a build by brushing or blowing it off. So, all of the options are correct. Now, disadvantages of an indirect route of SLS is lower density. Now, no support mechanism is required. Here, no milling or masking is required. Okay. No milling or masking is required. Here, this is done to produce parts which are considerably stronger. And the uncured material is easily removed after a build by brushing or blowing it off. This we know, we already went through. Next question. Which of the following are correct for green parts obtained from indirect selective laser sintering? Now, producing the green parts generally do not require any support mechanism. Green parts are free from internal stresses. Green parts are of high density. Green parts are nearly isotropic. The green parts are of high density. This is a wrong answer. In indirect SLS, no compaction pressure is applied. Green parts are of lower density. Distortion occurs during post-processing in a furnace, and this can also get damaged during cleansing, cleaning and handling. So, this direct SLS and indirect SLS is very important, and you need to understand what is the difference between the direct and SLS indirect methods. Like we saw here, this is the route for the indirect route, and a direct route only single structural powder is there. But here we have polymer binders, which are again removed through furnace processing. Okay. The next question, in indirect SLS, the material to be sintered consists of which of the following? The direct route of sintering, we have, sorry, it is the question about indirect SLS, the material to be sintered consists of which of the following? So the correct options are structural powder A and B, structural powder with a high melting point, binder powder with a low melting point. Now, direct route of sintering, powder material is, we have mixed powder technology, material to be, and where the material to be sintered consists of structural powder which has a high melting point and binder powder which has a low melting point. Suppose I also give the example earlier, Ni and nickel and tin. Here nickel, this melts at 1455 degrees Celsius. This is the structural binder, structural powder, and tin, this melts at 232 degrees Celsius. This is the binder powder. Thus, binder powder, low melting point, structural powder, high melting point. Okay. Next question. Which of the following is not a powder recoating system in the case of powder bed additive manufacturing process? So, this we know. Blade, roller, electrostatic, these three are powder bed powder recoating system, but flying optics is not a powder recoating system. So this is a scanning system. We discussed this concept over in this part where we discussed about the different types of recoater blade, roller and electrostatic. Also we discussed about doctor blade, soft blade, hard blade, etc. Fine. Next is, which powder material can be used in direct route of sintering in powder bed additive manufacturing process? Now, in direct route of sintering, we can use pre-alloyed or metal. Now, indirect route is, as we know, it is coated or mixed. And direct route is pre-alloyed, metal, polymer or wax. Now, this may be sometimes partially pre-alloyed or pre-alloyed. Now, direct route, here no sintering necks are formed, limited liquid formation. Okay, so sintering, now sometimes when the sintering necks are formed, there is sufficient liquid formation. Also, when these necks are formed, sometimes there may be this balling effect. So this is the necking occurs. Now, when this occurs when we have sufficient liquid formation. When we have limited liquid formation, what happens is this will merge with each other. Okay, but this balling defect will be formed. That is, this occurs due to low laser power, limited liquid formation with no sintering necks, and leads to discontinuous track deposition. Fine. Now we'll move on to the next question. Which joining mechanism applies sufficient heat and increase the temperature of the powder above the melting point, causing the powders to become liquid? Now this is melting. Now joining mechanism, we have three. We discussed liquid phase sintering, liquid phase sintering and melting. Okay. Now here it is asking, it applies sufficient heat and increase the temperature of the powder above the melting point, causing the temperature. Now melting, in melting only temperature is above the melting temperature. Now but in liquid phase sintering, we discussed many times that the melting temperature is between half of the melting point to the melting point, and that is in sintering. Okay, and liquid phase sintering also we have low sintering temperature. So the correct option here is melting process. Okay, so any more doubts? I think maximum questions from my assignments I have discussed, the concepts and everything. If any further doubts are there, please feel free to ask. Fine. If there are no further questions, we'll end today's session. Thank you all for attending the session. Let's meet again next week. We There may be an extra class next week on Saturday from mostly from 4 to 6 p.m. Please attend the session. This will be an extra class of 2 hours. We'll try to summarize what all we learned and some important topics from the first 6 classes. Yeah. Thank you all. Let's meet again next week.